Okay, good evening everyone. Welcome to another tutorial lesson, and it's radioactivity tonight. We're going to take a look at types of radiation, decay equations. We're going to have a run at half-life, how to do the basic calculations with half-life, and then some half-life graphs. That's a lot to get through in 30 minutes, so let's get cracking. Okay, so radiation occurs, or radioactive decay occurs when you have a large nucleus that is unstable. Okay, it doesn't necessarily have to be a large nucleus, but usually when we're talking about it in the context of GCSE physics, it tends to be a large nucleus. Okay, so let's grab ourselves a large nucleus. Check out the production quality. Continues to improve on the channel all the time. So here is one large nucleus with our protons in red and our neutrons in blue. And what we're going to take a look at here is what happens to this lovely little group of nucleons to make them undergo decay. Now, one of the big problems that you have with larger nuclei is that you have to get a balance of protons and neutrons in the nucleus. Too many protons, the whole thing falls apart. Too many neutrons, the whole thing falls apart. You need a pretty stable ratio, and that's one of the reasons that when you look at the periodic table, there's specific numbers that are associated with the stable versions of each of the atoms. Like those are the ones that are most likely to be occurring in nature, because anything less than that ends up decaying and turning into something else. So let's take our little unstable nucleus here and make him unstable, so we give him a wiggle about. And there's a few things that can go wrong here. Okay, option one is that we have some form of imbalance, that the ratio of protons to neutrons is just not right. Okay, that we maybe have too many neutrons per proton or something along those lines, or we have too much the other way. The ratio just isn't right. One of the best way to deal with that is to get rid of some protons and neutrons. And there are lots and lots of different ways to do that, ranging from fission to throwing out all sorts of random ones. But the most common by far is alpha decay. And that's because alpha decay is particularly energetically favorable. Whoop, that is the wrong one. Okay, so I need to copy in my little alpha particle if I can grab them. So an alpha particle looks like this. That we have two protons and two neutrons being ejected from the nucleus. And we're going to call this alpha decay. So this is alpha decay. Now, for your chemistry, you should know that two protons and two neutrons is a helium, but it's got no electrons. So it's not a helium atom, it is a helium nucleus. So we've got a few descriptions for this. We can call this an alpha particle, ALPHA for alpha particle. We can call it a helium nucleus, or we can just call it two protons, NuCleus, or we can just call it two protons and two neutrons together. Okay, whichever way we want to do it. But I like that. This is an alpha particle, and that is if we've got some form of bad ratio of protons to neutrons in our nucleus. This is likely to happen. Option two is that inside our nucleus we have too many neutrons, all right? And in order to deal with that, we have to undergo what's called beta decay. Now in beta decay, we target this, or one of the neutrons. Okay, so one of the neutrons, let's go for this one here. He goes from being a nice blue neutron and then ends up filled in and becomes a red proton. Now, suddenly we've gone from a neutral neutron to a positive proton, and that's not allowed by physics. There's something called conservation of charge. You can't just generate a positive charge out of nowhere. So when we make a positive charge, our neutron goes from being a neutral neutron to being a positive proton and a negative electron. Okay, so the negative electron then, because it's not allowed in the nucleus, and there are reasons for that, to do with things called something called the Heisenberg uncertainty principle, for those of you who like reading around the topic, that the electron cannot remain inside the nucleus, so is fired out. And this high-speed electron we call a beta particle. Okay, but it is essentially a high-speed electron. Now you should be at this point saying, wait a minute, aren't all electrons high speed? And you're absolutely right. This one though is going like a bat out of hell, even by electron standards, and most importantly, it is not bound to a nucleus. So it's not orbiting any form of atom, it's just it's coming out of there and it's flying. Okay, it'll maybe eventually run into another one, but and then get captured. But at the minute, it's a free electron. Okay, and we call this process beta decay. Now, usually after beta decay and alpha decay, we've had things shot out of the nucleus. And if I were to hold like a cannon or a gun or something like that there and fire it, not only would the bullet go one way, but there would be a recoil into me. There would be some energy sort of left behind me. And that tends to be true in the nucleus as well. So when you get alpha decay and beta decay, associated with those, you've got a pretty high likelihood of getting a third type of decay. Now this one doesn't actually do anything to the structure of the nucleus, but what it does is it helps dissipate too much energy. So if your nucleus is in the situation where it has far too much energy and it needs to kind of relax itself, it's a bit like like a ball sitting on top of a really pointy hill. The forces of nature will make it roll down the hill to a position of less potential energy. This is kind of the same, that our nucleus is a little bit excited and needs to calm itself down. It needs to release some energy. And we do that by something called gamma decay. Now, no fancy graphic for this one, interestingly. There's no particle involved here. There's no piece of material that comes off. So what we get is this sort of symbol here, that we get a wave of energy, like it's a little ripple that comes out, a little ripple of energy that comes out. It's nothing particularly that you can grab or look at, just a packet of energy. Now we know it's there because it has effects on stuff, and gamma radiation, particularly dangerous type of radiation, but we'll get into that in just a few seconds. So gamma radiation is, we get a gamma ray. Notice we don't see the word particle there because it's not a particle. It's some energy, and it's just a packet of energy. For the super fancy amongst you, you can change the word packet to photon if you want, but probably a good idea to avoid that term until a little bit later in our education, a couple of years from now. All right? Happy? Good. Excellent. So what we're going to do now is we're going to move on to what these types of radiation do, how you stop them, how you get on with them. Okay, so alpha radiation is, because it's an alpha particle, it's a helium nucleus, it's 2 protons, 2 neutrons, and as a result it carries a 2+ charge. Beta decay is a single electron, so it carries a 1- charge because it's an electron, and gamma, because its energy, has no charge. So we've got 2+, 1- and 0. And this kind of accounts for their behavior, that an alpha particle traveling through the air is not going to get too far. And the reason it's not going to get too far as an alpha particle is, as soon as it encounters something else, it's just going to go, I'll have those electrons, thank you so much, and yoink electrons from something else that it sees. Okay, so as it travels past an oxygen, it'll go, thank you, I'll have that. As a random bit of nitrogen floating about in the atmosphere, yoink, I'll have a bit of that. Okay, so very quickly, our alpha particle, which is kind of dangerous looking thing, becomes helium. It just becomes a regular helium atom, which is not particularly dangerous unless you're massively scared of high-pitched voices. It's not a problem. Okay, so and it doesn't take too long for that alpha particle to do that. So alpha particles, super dangerous at close range. Okay, because they can nick stuff from your body, they can nick electrons from inside your cells. That's bad news because you're basically a chemical reaction system. So if you start nicking electrons here, there, and everywhere, things can go wrong in your body pretty sharpish, and it doesn't take too much to go wrong in cells for them to go mental and start dying all over the show on you or turn cancerous. So alpha decay, in theory, is probably the most dangerous one here, but in practice isn't, because it never travels far enough to be any real danger to you. Like unless you're planning to eat this or inhale it, you're okay. You're fine. All right. Beta decay, on the other hand, it'll get a lot further. You would think that's weird. Why is that? Because it's only got it's got half the charge of an alpha particle. Why does it not just get twice the distance? That makes sense. But because it's an electron, when it meets other atoms, it sort of has to persuade its way in. And most other atoms are generally quite happy with what they've got. They're electronically stable. They don't want another electron in their shell messing up their lovely octet rule or anything along those lines. So they end up traveling quite a distance before they find a little particle to go, oh, okay, I'll have you, thank you very much. And gamma radiation, well, because it's got no charge, and travels at the speed of light because it's a packet of energy, and energy has a habit of doing that, will travel an insane distance. In fact, it doesn't have a range really at all. It's going to go until it's stopped. So in air, it's going to just keep on going and keep on going and keep on going and keep on going, right, until it hits something. This is, whilst not actually particularly harmful to you as a single ray, the fact that there's lots of them produced and getting away from them is very, very, very difficult. It's actually, in reality, the most dangerous. It's a bit like, imagine that the alpha particle is a giant shark. Okay, it's super dangerous, but it's absolutely no danger to you as you're sat in your house. Unless you have a giant aquarium in your house, it's completely safe. Right? Whereas a gamma ray is a bit like a toddler. It can get to you, it's kind of cute, but 10 million of them determined to hurt you are going to take you down. I don't care who you are. Right? And beta decay is somewhere in between. So here's what we want. We want to make a table kind of dangers, and you need to learn these dangers off. So we've got our type of radiation, and then we've got alpha, beta, gamma, and then its range in air, and then what it's stopped by. Okay, so we want this type of thing. Okay, so if we have alpha, and then we have beta, and then we have gamma radiation. Gamma. Okay, in air, so range in air. If I could spell, that would really help this evening. So alpha range in air is a few centimeters, because it'll only go a few centimeters before it manages to get a couple of electrons, and then it stops being an alpha particle. It just becomes helium. Beta, maybe a few meters, which is 100 times further than the alpha particle, even though it's got half the charge. But it's the opposite half, which makes life strange. And gamma radiation is theoretically, infinite. It'll just keep on going. Okay. Now, what we want to stop by, okay, so because we don't really want radiation in us, it does things called ionization, which can give you cancers, can make you very, very sick. We don't want that. So how do we stop an alpha particle? We stop an alpha particle with a thin sheet of paper. So not massively dangerous. Okay. Beta radiation we stop with a few millimeters of aluminium. Okay, our American viewers are having problems here, but this is how you spell aluminium, A-L-U-M-I-N-I-U-M. And then gamma radiation stopped by, we want several centimeters or inches, because we'll give something to our American viewers. So several centimeters of inches of lead, which is the most dense material that we can kind of readily get our hands on, or several, S-E-V-E-R-A-L, several meters of concrete. And this is a table that you should have, and that should be what you want to do. Okay, absolutely right in the comments there. Gamma radiation is used to kill cancer cells because of the fact that it's so dangerous to living cells in general, but it has the habit of, when not directed correctly, not focused correctly, it can cause cancer as well. All right, so on we go to our next little bit. Then we want to do some decay equations. Now, decay equations are, generally speaking, not too bad. If I start with material X, right, and it undergoes radioactive decay, then what we need to do, I'm going to make this a little bit bigger for us because we want to write all around this. Okay, so material X. Let's say it has a mass number of A and an atomic number of Z, and that, again, that's standard stuff for our exam course. So the mass number is A, even though you would imagine that the atomic number is that, and the atomic number is Z. Then when you undergo alpha decay, what happens is you always get an alpha particle. So we just pop that at the end. So we do that in symbol, and we type a little alpha. It's like a fish. Okay. And an alpha particle, as we said before, is always the same thing. It's 2 protons, so it's got an atomic number of 2, and it's 2 neutrons, giving it a mass number of 4 because there's 4 things in its nucleus. That always goes in. So when you see an equation for alpha decay, you've got to have this at the end. 4 to alpha. You can put He here as well. That's fine. You can call it helium if you like. Nobody's going to take you to the farm on this one, but that's the best thing to do. Okay, so then we end up with, well, what happened? We had a nucleus that lost 4 mass and lost 2 protons. So whatever I make after this is going to be A take away 4 for its mass number, because it's lost 4 mass, and Z take away 2, because it's lost 2 protons. Right, now, because the atomic number has changed, and from your study of the periodic table, I'm hoping that you know that that means that the material has changed. Then this stops being material X and becomes material, we'll call it Y, for the sake of it. So everybody loves a bit of algebra, and this is how it goes. Right. So let's pop a couple of numbers in. Let's make up some imaginary stuff. I don't have any pre-prepped equations for this, so we're not going to use proper symbols or anything like that there. But let's say we have mass number 215 and atomic number 87. And I haven't memorized my periodic table, so I don't know what number 87 is. But let's assume that this undergoes alpha decay. If it does, it means there's going to be an alpha particle produced, 4,2 alpha. So this must have A minus 4, which is 215 take away 4, which is 211. And this has to have Z minus 2, which is 87 minus 2, which is 85. Okay, so this one is number 87 in the periodic table, and this one's number 85 in the periodic table. And you can see they're different. Now, in your GCSE exam, you do not get a periodic table, therefore you will not be expected to name or letter any of these. But you will be expected to be able to take information and fill in the remainder. Okay, so I could give you 215.87x undergoes alpha decay and expect you to fill in these 4 numbers. And it should be the case that the mass numbers on the right hand side of this equation add up to the mass number on the left hand side, and the same is true for the proton number. So 215 equals 211 plus 4, and 87 equals 85 plus 2. Right, in exactly the same way, let's take our material A, our material AZX here, and let's have it undergo beta decay. Now, beta decay, what happens there is we get a beta particle produced. Now, it's a bit strange because a beta particle is an electron, which makes life interesting when you're trying to give it an atomic number. Now, the atomic number you'll have been taught as the number of protons in the nucleus is better thought of actually as the number of positive charges contained in whatever it is that you're looking at. So a beta particle actually has an atomic number of -1, because it doesn't just have no positive charges, it has the exact opposite of a positive charge. So therefore it has -1. And it has a mass number of 0, because the mass number is the total number of protons and neutrons, and it's an electron, so that number is 0. Alright, now that leaves us then with the exact same situation. We want to figure out what happens here. Well, because this side has to equal this side, we end up with our numbers, that this is just A, because A equals A plus 0. And on this side we have Z plus 1. That's interesting, because Z plus 1 plus -1 is back to Z again. Notice our atomic number goes up. That feels odd, but then remember what happened. A neutron turned into a proton. So suddenly we've got 1 more proton, so my atomic number goes up, but my mass number remains the same because I lost a proton, lost a neutron, gained a proton, so everything is massively speaking the same, but we have an extra positive charge in our nucleus down here. Because our atomic number has changed, again, we change from material X, and we'll call this material Z this time, just to make sure that we don't, or we'll call it actually material B. T would be better. Okay, so because just not to confuse it with our material from last time. Right, let's knock in some real life examples in this one. Or not real life examples, but real number examples. So let's say I have material X. Let's give it 197 and 76. Then we go, what does A have to be? Well, it has to add up to 197 on this side. So 197 plus 0 equals -1. I should put my plus signs in there. That's tardy of me. I was sorry about that. Dear me. Dear me. I can feel the dislikes happening now. There we go. Whereas down here we have 76 has to equal something plus minus 1, so that has to be 77. Because 77 add minus 1 is 76. And that should be the decay. Right, the last one, and in the interest of time, I'll probably not do an example on this because it's ridiculously easy, is gamma radiation. So we're going to pop this and we're just going to edit it as we need. So in gamma radiation, we don't get a beta particle produced, we get a gamma particle produced, which is one of these. Now, since a gamma ray is without mass and without charge, and it's just a bit of energy, then these numbers are 0 and 0. Which sort of makes this kind of easy to work out, because we end up with A and Z again, because A plus 0 is A, and Z plus 0 is Z again. And this is where life gets interesting. Because the atomic number has not changed, we end up with X again. The material does not change. There is no change of substance here. It's just a release of energy. It's the exact same nucleus. Now, occasionally you will see this written, that this one over here gets a little asterisk placed beside it to denote that this is kind of energetically unstable. So you got X star goes to X more stable, just to show that this isn't some weird reaction where nothing happens. This denotes an instability. Right, is that okay? Is that okay? Are we all happy? Good. Good. Okay, on we go. So we're looking now at half-life. So if I've got a radioactive material, then the likelihood is that somewhere in my material I have several, I would say millions, but millions is a gross underestimation. Several, even saying hundreds of billions is a ridiculous underestimation. We have lots and lots and lots of particles. Okay, and they should all be roughly identical, but let's just imagine that some are closer and some are further away from the screen. That way my terrible drawing skills don't come out. Now, if I watch these, every single one of these is theoretically unstable. Okay, they are going to radioactively decay at some point. When? I have no idea. I could sit here and watch this little guy here, and I could watch him, and within 2 seconds of watching him, boom, out comes an alpha particle. Or I could sit and watch him from now to the end of my life, and he never decays, and I don't know anything about it. It's a completely random process. It's like rolling a dice, or a die, grammar please, but we're going to call them dice from here on, and I know it's wrong, but I don't care. I know that there's a possibility I get a 6, but I've no idea when it's going to happen. But because I've got a ridiculous number of these things, I can apply statistics. And statistics work really, really well for large numbers. For this large number, they're almost perfect. And by almost perfect, I mean perfect. That it's so ridiculously precise that we can use this to date things very, very, very accurately in radiocarbon dating and stuff like that. So the game goes like this. If I roll a dice, I don't know if I'm going to get a 6 or a 2 or a 5. Any individual throw is completely random. But if I throw enough dice, I know that 1/6 of the time I'll get a 1, a 6th of the time I'll get a 2, a 6th of the time I'll get a 3, and so on. And this is where half-life comes in. That I don't know when any of these individuals are going to decay, but what I can do is I can tell you how long it's going to take for half of them to undergo radioactive decay. So I can't predict where I'm going to draw these lines, I have no idea, but I can time how long it takes half of them to go. And once I've got that half, I then know that that is the same number for the next half. It's the same amount of time every time. And it's not just for half, it's for any percentage, but half's nice and handy. And that's what half-life is. Okay, half-life is the time taken for the activity of a substance to fall to half its original value. I'm going to pop that on the screen because that is a definition that we have to know. So half-life is the time taken for the activity, and that's a word, of a radioactive material to fall to half of an original value. Let's unpack that for just a second. The key word here that we probably don't know is the word activity. So I'm going to get my highlighter pen out and grab that. Okay, we want a definition for this. What's happening there? What is activity? Now, activity in radiation is a very, very, very specific term. It means the number of decays, that's alpha, beta, or gamma emissions, per second. And it's measured in becquerels, BQ. And that just means decays per second. Back in the day when you could name things, when you made up stuff as like decays per second, I'm calling that after myself. And like I said, in class, I don't know why anybody didn't come up with the unit of Urma. It's just brilliant and genius. But no, just give it a name. Give them your name, even if your name's Becquerel. Right, and then this other little bit here is an important word as well, of an original value. Not the original value, because we don't know what that is. But as soon as you start timing, if you know how much you had to start with, the time it takes to get to half of whatever you started with will remain the same. So if I start at 200, the time it takes me to get to 100 will be exactly the same as if I'd started at 40 million and waited to go to 20 million. And that's what half-life does. It allows you to predict the time. So let's try a standard question. A standard question would look something like a material has an activity of, let's try 600 becquerels, and a half-life of 60 seconds. No, not use 60 because then we've too many sixes going on. So a half-life of, let's just do 10 seconds, keep life easy. How long until the activity, ACTI, I tell you what, my spelling is ridiculous this evening, activity falls to, let's do 75 becquerels. Okay, that'll be small q. Right, so what we do in this situation is we kind of try and logic this through. Well, if I start at 600 becquerels, let's go 600. After one half-life, I'm going to have half of that, so that's 300. Then after another half-life, I'm going to end up at half of 300, which is 150. And then after another half-life, I'm going to be down at 75 becquerels, which is exactly what I wanted. So how many half-lives did I go through in that? Let's just check. So I'll grab my pen, this one. There we go. That's one half-life, two half-lives, three half-lives. Okay, so 1, 2, and 3. And since we know that each half-life was 10 seconds, and we've gone through 3 of them, it's a nice simple 3 times 10. The total time for that is 30 seconds. Alright? And that's half-life calculation. Now you might have to do that backwards. You might have to say a material has been sat in the lab for 30 seconds. It now has an activity of 75 becquerels and a half-life of 10 seconds. What did it have 30 seconds ago? And then you go, right, well, if I had 75 now, then 10 seconds ago I had 150, and 10 seconds before that I had 300, and 10 seconds before that I had 600. Okay, but there's no massive equation required here, though there is an equation that tells you how to do this. We'll do that at A level. This is pretty much as you get, because you can imagine this becomes a little bit more interesting when how long until the activity falls to 68 becomes an interesting question, because you can't just do it this way. You need some form of maths that does that, and there is maths that does that. We'll teach you that next year. Right, so an activity has, so we've got that sorted out. Now what we want to do is take a look at our last thing, which is half-life graphs. If I plot this, if I plot 600 against that, so let's just really quickly do that because we're running out of time. It's nearly 9 o'clock and I don't want to keep you too long. Let's do a time. So at 0 seconds here, let's grab 10 seconds roughly there, 20 seconds is about here, and 30 seconds is somewhere around there. And we were up at 600 to start with, 600, and then we went to 300, which was about half that, and then we went to 150, which is going to be around about here, I reckon, and then 75 is going to be halfway in between there and there. Then that's what we've got. Okay, except you'll do it as a proper graph, that you'll have proper scaling, and not just 4 things. You'll have 25, 50, 75, 100, 125, 1, and so forth. Up you go. Okay, plot our points on, so grab small things. And of course, in exams, you are very sensibly always plotting with a small x, because your exam gets scanned and sent away. And when that happens, any dots just disappear, because scanning is terrible. Okay, so make an x. And your graph will end up looking like this. Okay, that as you draw your curve of best fit, now this ought to be interesting. you get a kind of downward sweeping curve effect that'll go onto there. And all half-life graphs look like this, kind of downward sweeping curve rather than a straight line through the origin or anything along those lines. Now, how to get the half-life from a graph, and this is more of a triple award question than it is a double award question. What you do is you pick a number. Okay, so let's say I didn't have all this. Let's say I picked 500, which is around about here. And I measured that down. Okay, so I've got 500 and the time at 500. Okay, read that off. Then what I need to do now is go, right, how long does it take to get to 250? So I go to 250, cut across, and then cut down again. Now, even from my crap graph, we can see that that distance there to there is roughly 10 seconds. A little bit more, or a little bit less in my graph because it's super rough, but it should be 10 seconds. Because the time it takes to get from any value to half of that value is always going to be, for this graph, 10 seconds. And you need to be able to pick that out from a graph in an exam. And the easy way to do it, just pick a number, any number, pick something handy, people. Don't pick like 57.39. Pick something like 100. Okay, go to 100, mark off what the time is, then go to 50, mark off what the time is. The difference between those two times, that's your half-life. If there's lots of marks for the question, do it twice. Get an average, make sure that you're absolutely content with your answer. Repeat for reliability. Alright everybody, that's us, whistle-stop tour of radioactivity and half-life. We still have nuclear fission and fusion to cover. We'll do that in a future live stream because they're big 6-mark questions that require lots and lots and lots of work to do in that. So I'll get you that one maybe in a couple of weeks time. But if you want something more urgently, you know what to do. Get into the comments section below. Let me know what you want to learn and what's causing you the most difficulties. Alright. As always, there are some questions relating to this topic in the description below. Click that, you'll get a PDF. I didn't put the mark scheme in this time because I think some people are just copying the answers off. So let me know how you get on with those questions, which ones were easy, which ones were hard. Alright, thank you so much for tuning in. I appreciate that I was up against excellent TV programming this evening. So thank you so much and good night everyone. I will see you next time. Physics rocks. It's true. And Tegan gets a shout out for her broken finger. Poor girl.